Hey guys, Mr. Smith here, and in this video lesson, we're doing a bit more problem solving with linear systems. We're going to look at mixture problems and speed, distance, time problems. And again, I mentioned this in the last video, but it is impossible for me or any teacher to give you an example of every single type of linear systems problem under the sun. Or every single mixture problem or every single speed, distance, time problem. The best we can do is give you a general example that hopefully equips you a little bit that you can go apply these later on. But I think these two examples will help for sure. So here's our first one. So this is a bit more of a relevant problem. So Miss Warner is a chemistry teacher, and she has a bottle of 5% acetic acid and a bottle of 10% acetic acid. So if you don't know what that means, it means in the first bottle, 5% is acid and 95% is water. In the second, 90% is water and 10% is acid. So there's more acid. It's a stronger acid. It might be more harmful if it comes into contact with you. But for a science experiment, she doesn't need 5% or 10%. She needs to make a mixture that's 8% acetic acid. And she needs 250 milliliters of the 8% acid. So if you can imagine, she has to pour in a little bit of the weak acid and pour in a little bit of the strong acid. And she doesn't want to just eyeball it. She's a chemistry teacher. She needs to be precise. We need to know exactly how much of the weak acid and how much of the strong acid we need to mix in. So as usual, our first step is to assign variables. So this question's pretty clear. How much of each should she use? We need to know how much of each type of acid. So I think in this question, it makes sense to use just X and Y. Let's let X represent the amount of 5% solution. And I might add in milliliters. We're measuring in milliliters. And then a similar statement just with Y. And let's do Y for the 10%. The amount of 10% acid or 10% solution. And again, it's in milliliters. So in this mixture problem, I've given you a lot of structure to help you set this up. And in practice, it's my hope that this just helps you do future mixture problems. So before we create our equations, I have a little table for us to make. So we said that in our mixed solution, we're letting X represent the total amount of the 5% that's going into our solution. And Y is the total of so X is how much we're pouring in of the weak. Y is how much we're pouring in of the strong. And in total, there's 250 milliliters. So that row there just keeps track of the total amount of each that we've put in. Now, let's keep track of the total amount of acid. Remember I said that a 5% solution means it's 5% acid and 95% water. Well, how much acid is in there? How do you find 5% of something? Well, to find 5% of something, you make 5% a decimal, right? 0.05, and you multiply it by that something. The amount of acid in that first bit is 5% of X, or 0.05X. And the amount of acid in the second mixture, well, if you want to find 10% of something, you multiply by 0.1. 0.1 times Y. Now, how much acid is in the 8% mixture? This is what I would say tricky part of mixture problems. Everything I've written down right there was given in the problem, but 8% of 250, which I think is 20, but I'm going to double check on my calculator. That 20 is nowhere to be found in the problem. 8% of 250, I had to do that myself. So let's bring up my calculator. 0.08 times 250, it is 20. So The amount of acid in the mixture is 20 milliliters, and then it'd be 230 milliliters of water. Again, that's something you're going to have to just kind of remember as you do mixture problems. Again, 20 doesn't appear anywhere in our question, but now we're good to go. She needs 250 milliliters in total. So equation 1 would be, well, I'm pouring in X of the weak stuff and Y of the strong stuff, and it has to give me 250 in total. And then for our second equation, well, in the weak acid, I'm pouring in this much acid. It's 0.05x. From the second guy, I'm pouring in 0.1 times y. That gives me the amount of acid in total. And altogether, that has to add up to 20 milliliters of pure acid. And so we've got our two equations. And honestly, guys, every mixture problem sets up exactly like this. You have your two different solutions adding to the total, here 250. And then you have your percentages, so 5%, 10%, and then the percentage of the total mixture. In this case, it's acid, but you could do problems like these with interest rates in a bank account. There's so many different types of problems you can do setting up with mixture problems. But now that we have our two equations, let me just write them down on the next slide, and then we'll solve the problem, choosing an appropriate method. So x plus y equals 250, and 0.05x plus 0.1y equals 250. Equals 20. Caught myself there. So let's think of what method would work. I see an x and a y all by itself. So substitution would be a great method. But elimination could work too. I can think of an easy way to match the y's up. What do you have to multiply equation 2 by in order to match it up with equation 1? If you multiply it by 10, you get, well, for x, you get 0.5 times x. 10 times 0.1 is just y. And 10 times 20 is 200. That's just equation 2. And I can just rewrite equation 1, x plus y equals 250. So in my opinion, using elimination would be a good idea here. It wasn't hard to match the y's. And now I can do, I'll do equation 1 minus equation 2. X, so that's 1x minus 0.5x gives you 0.5x as well. Y minus y is 0, and 250 minus 200 is equal to 50. And if I divide both of those sides by 0.5, 50 divided by 0.5 is 100. And we have 100 milliliters of the 5% solution. Most of you guys could probably use mental math here and figure out how much of the other solution is there. But let's be complete about this and just get a nice solution. Let's sub x equals 100 into equation 1. 100 plus y equals 250. So obviously there is 150 milliliters of the stronger solution. So for a concluding statement, we can say that Miss Warner needs 100 milliliters of 5% solution and 150 milliliters of 10% solution. And I can tell you, because I work in a math and science department, that chemistry teachers are doing these kinds of calculations in order to produce the strength of acid they need for a particular experiment. So yeah, very useful problem. This is just one type of mixture problem, but the strategies we employed can be used for any mixture problem. Let's do one last example together. We're going to do a speed, distance, time problem. So here we have Bort. He's on a canoe trip. Now, it took Bort 2 hours to travel 12 kilometers down a river. And when we say down a river, kind of meaning like Bort is paddling with the current at his back. So it's nice and easy. The current's moving him forward. He's paddling. That helps him move forward even faster. But when he has to come back, he's against the current. So he has to work a lot harder against the current to come back, and it's going to take him longer to get back. Most of us probably have some kind of experience with that. Not necessarily paddling, but knowing that if you're working against the river, it's going to be harder. It's going to take you longer to get back. So what we want to find is how fast can Bort paddle, and what's the speed of the current? So two things we're trying to find. Let's write let statements. Let's let P represent paddling speed. And let's let C represent the current speed. So we have two situations here. One where Bort is paddling downstream and back up. So I often, if I'm helping students with the speed distance time problem, I say make a table like this. And at the very least, it can help you get organized. Going downstream, then just record the distance, speed, and time, or expressions for those for each one. So going downstream, you travel 12 kilometers. Upstream, it's the same return trip, also 12 kilometers. The time, it took 2 hours going downstream, and it took 3 hours going upstream. Now, what should we put in for the speed? So think about, I'm going to use the diagram as an example. So think about if we have the current going downstream, and if Bort is paddling downstream too, then the speed of the current and the speed is paddling, they're going to work together and they're going to add, and his total speed will be P plus C, his paddling speed plus the current speed. Going back, the current is still the same, but he's going to have to paddle against the current. And the speed he goes up the river, it will be the difference, P minus C. So I think I just heard my wife call me. So if somebody barges into the room, we're just going to roll with it. So again, going downstream, they work together, you add. Going upstream, paddling and current work against each other, so we subtract. And now we're ready to set up two equations, because we know from earlier grades, or just common sense, that distance equals speed times time. So if we plug those in for the downstream situation, the distance 12 equals the speed, which we said was P plus C, times 2. And I'll leave it like that for a second. Going upstream, our equation is distance equals speed, P minus C, times time, which is 3. Now, we're going to clean both of these equations up a little bit. So there's several ways to do it. I'd say one is easier than the other. So if you let's do it right here. If I just divide both sides by 2, I get 6 equals P plus C. That's an easy way to simplify that equation, right? 12, we have a times 2 over here. Let's just divide 12 by 2, right? If you do the same thing on the other side, you get 4. 12 divided by 3 is 4, equals P minus C. So complicated looking question, perhaps, but the linear system is actually really nice to work with. So let me rewrite that equation down below in our solution. So we have 6 equals P plus C. I might write that as P plus C equals 6. Those mean the same thing. And then we found that P minus C was equal to 4. We need to solve that linear system. Guys, this linear system is tailor-made for one of our types of methods. You want to pause the video and think of a strategy, and you can unpause when you're ready. But I think elimination is perfect for this one because both variables match. You can eliminate any one of those easy. Let's eliminate the C's by adding. We add equation 1 plus equation 2. We get 2P C and negative C add to 0, and 6 plus 4 is 10. Why did I circle the 4? I actually don't know. Let me erase that. There we go. All right, let's finish this off. So that gives us that P equals 5. And let's sub P equals 5 into any one of those. Looks easy to work with. So we have 5 plus C equals 6. And I can see that C is equal to 1. So we found that Bort, I'll just erase that, Bort paddles at 5 kilometers per hour. And the current is 1 kilometer per hour. Bort paddles at 5 kilometers per hour. And the current is 1 kilometer per hour. All right, so we've done a mixture problem, and now I've shown you guys how to try to set up a speed, distance, time problem. Now, I will say that those are definitely not easy. We are problem solving here. They can be challenging at times. So you guys have these examples to go from. You have examples in your textbook as well as online resources to help you if you're stuck, or ask a friend or ask me. Again, the most challenging thing is just building up experience to actually setting up the linear system. Solving the linear system shouldn't really be too hard anymore. Either of the linear systems we solved here, none of them were very complicated, but the setting up was the challenge. So you need to practice and get experience, because as you solve more and more problems, eventually you just run out of new types of problems to solve, and they all start to look similar to ones you've done before. But you only get to that spot by practicing and kind of building up your experience. So I'd really encourage you guys just to practice, stay positive, get help when you're stuck, and just build up your experience. Guys, that concludes our lesson, our unit on linear systems. So I hope you've enjoyed that learning. I certainly enjoyed, I definitely enjoyed making these videos. I'm sure in class I'm having a good time working with you guys. We'll be wrapping up the unit together and then starting another unit. So stay tuned for the next little video series. Until then, hope you guys are staying well. Have a great day, and we'll see you soon.